Okay, good. So yes, just message something just to say that it's on his side. Yeah, so this will be the GitHub page where we'll maintain everything, including our labs. And the lab we have, most of the tools, actually all the tools except this CPP Sim Lite will be installed already in the root location. So you don't have to download it from anywhere. It's already installed. Um, the only tool you need is the CPP Sim Lite, which is also in this GitHub repo. Uh, 1 second. Did somebody raise the hand? I just saw, I don't see anything. Okay. Yeah, just text us if you have a question and we'll unmute you. Yeah, so the only tool which is not there as part of the installation is the CPP Sim Lite, which basically has the schematic editor and the GitHub, I mean the Python API. And that when you pull this GitHub page, you'll get that as well. And we'll put the labs and everything in this page. And all the information will be maintained in this README file. So you can see this readme.md, and this is where we're going to maintaining all the course information. So let me just quickly go through what info I have here, so that way you can come back to this whenever you need it. So the course content, Introduction to Digital Design. So that was last week by Puneet, which is done. And for the next 3 weeks, what we're going to start is the custom CMOS VLSI design part of it, the digital VLSI design part of it. And starting today, we'll introduce you to the VLSI design flow and CMOS processing. And then tomorrow, I'm going to review some of the basic circuit theory and start with just the passive integrated devices in circuit design, in integrated circuit design. And then and then we'll start with the MOS device physics, where we'll go deep into the device physics part of the MOS device, which will be basically the main device we'll be working on in this course. And then the inverter characteristics, static and dynamic. And this inverter characteristics plus the MOS device is probably the single most important thing in this course. If you're going to take anything away from this course, you have to take, because everything is built upon this. Your complex gates, your standard cells, your D flip-flops, everything is based on inverters. So don't think, oh, it is inverter characteristics, why do I need to know? I'll just know advanced stuff. Everything is based on this. So you just make sure you pay a lot of attention. So if you want to take away anything from this course, you want to take the device physics and the inverters. And see, if you know the inverter characteristics and MOS device and the basic circuit theory, which is in this most part of this course, and if you're able to use basic EDA flow, doesn't matter if it is open source, like what we're going to use, 99% of the places you're not going to have any issues with your interviews and placement, because you guys are undergraduates, right? You're not 15-year experienced guys. They're looking for you to know Virtuoso Excel, DC, and all these tools. So if you have your basic fundamentals covered, that'll get you, like I said, 99. But you have to know well. It doesn't mean that you mugged up something and they twist one question and then you don't know. So you have to obviously know very well. So we'll try to go at a decent pace. Sometimes it could be fast. You just have to. We have to, like as I said during the introductory part, when people were complaining, oh, it's too simple, it's too hard. Like I said, we have to strike a balance. We can't, target everyone in this course. It's just very difficult to do that. But having said that, I'm not expecting any prerequisite other than what you have done in your, high school or like in your first 2 years. That's it. If something seems to be, you know, to be appearing difficult, you can ask some questions, but it's nothing to do with your prerequisite. I remember people saying, "Oh, what's the prerequisite? What's the prerequisite?" There's nothing to do with it, because some of the fundamentals might be the first time we are introducing. So you just have to get used to it, ask questions, and you're still not able to follow. We're going to give you a ton of material to follow, the videos and a lot of the reference materials. So you just have to kind of, work offline. We can't adhere to everyone during the platform. Having said that, if there is something simple and you just can't follow it, you should ask the questions. And like as I said during Puneet's class, that you have to ask specific questions, but at the same time, don't ask the specific questions in 3 million different ways. Just ask the fundamental question. If you're still not able to follow, we can take it offline. But don't ask, please repeat what you said last half hour, right? I mean, that's not going to help. So we'll do our best to make all these fundamentals clear to you. Stop us anytime you don't understand, but at the same time, don't just like interrupt every 5 seconds, because usually I will cover something and the end of that concept, I'll stop and I'll keep asking questions. So just have patience. And if you still feel that I went to the next topic and you still didn't understand, definitely ask questions. I put some references here. I think these two books, this is the third edition. I gave you the link for the third edition. This is a great textbook. This is the most popular one people use, the Kang's book for textbook. But this is my favorite actually, because it just covers everything very concisely, goes to the very depth without, using a lot of words, equation, and so on. So this is what, for at least for the CMOS part of it, I'll use it as a text material. And these are all great references. Kang, Yumura. Yumura is probably the best reference for when we cover threshold voltage. That's probably the best reference. You're not able to access to the link of the book. Is it everyone? Is anyone able to access it? Just say one of you say yes or no. Is nobody able to? Yes. Okay, so Sumant, it's something on your side. Looks like everyone is able to access it. So something on your side. I can't put those links on this because this is public domain and those are copyright materials. So don't put it somewhere in public domain. Don't put it in your, website or blogs or anything like that. That's why I send it on WhatsApp. So download it and keep it, or at least keep the link. That's a Dropbox link to my Dropbox. So you should be able to access it anytime, or best you just download it and keep it to you, because these references you can reuse rest of your life. Like Kang, that was the first book I used to teach back in '96, and people are still using it. So these are very classic material. Hodges is same thing. Baker is a great reference book. This is not good textbook because it's just very, very voluminous. So it's not a great textbook, but it's great reference for if you want to look for some material. So while, as we go through the materials on this page, GitHub page, I'll keep giving references to some of the sections or chapters, but not always. So some of it, you have these references, you just have to get it. The PDF for these, I'll send a link as well to you. The Kang actually is the one I sent you is second edition. It's actually not the fourth edition, although I've given you reference as fourth edition because I don't have a PDF copy of fourth edition. This one actually I cut my book, and this one also I didn't get it anywhere. So I actually cut my own book and scanned it on Sunday and send it to you. Maybe I'll do that here, but the second edition actually pretty much has everything you need. So Imra also, I have an old PDF, and Baker and West, I have the newer one. So I'll send the PDF again. These are copyrighted materials. It's okay to share personally, but you shouldn't put it on your blog or anything like that. So that's why I haven't put this link. But any public material, I'll put the links here as well, so that way you can access it here. Just the copyrighted materials I can't. Okay, so that's sort of, yeah, so I have an announcement section here. So anything we announce on the WhatsApp, I'll try to put it as much. If I miss something, you can ping me, like the registration one. I put a link here. So in case somebody, because in WhatsApp, it's like, a, you know, kind of a river flowing. So sometimes in the search, I sometimes find it not as good. So that's why some of the reference material, will just put it here. So that way you can just always come back here and refer to it. So I put this, you don't have to worry about it right now. Uh, all the tools you'll be using, how to set it up, and some quick start guides. I'm putting it here. So that way you can just, you know, come back and refer to them. Like here, there's the ngSpice reference manual. There is actually a great appendix, the appendix A in Hodges' book. You have the link to this book now. That's probably, if any of you or most of you are not well versed with spice at all, start with the appendix A of Hodges. That's a great book to start. So the labs, we are planning to start on Friday. Initially, I was planning to start it next Monday, but then I realized that if I started on Friday and we at least get you introduced to it, then you have the weekend to try it out. For the labs, we are paying a lot of money because this is all web-based. Like before, we used to ask people to download VirtualBox and, you know, load OS and all that. It's you know, it's not a grueling process, but it's more of a hassle for us because every person has some or other problem, and, you know, with 60 people, it's just difficult to manage that. So that's why, you know, we spent some money. So there is a company in Bangalore which creates these Linux instances. So essentially what you get is a kind of a low power, but enough to run your tools. A Linux desktop, which is accessed completely through the website. So you don't have to worry about anything at all. You just go there, sign in, and you'll have a Linux workstation for you. And you can start working for these 2 weeks. And take this opportunity, guys, learn these tools. And if you are not used to Unix or Linux, this is your moment. Just like put all your effort and learn. This is the biggest complaint I get from companies, is that the students who are coming out recently. So when we graduated, we only knew Unix. We hardly knew Windows because everyone worked in Unix. But people are working on Windows environment right now. But all the CAD tools and everything in VLSI is all Linux based. Okay, it used to be Unix based. Now it's all Linux based, which is pretty much the same. So you have to get really familiar with Linux. Okay, so I'll give you some good, you know, quick start guide to start with Linux, and especially a editor called Vim, which we will be using a lot. You can use some other editor if you want to, but that's again editor which is used very extensively in VLSI. Okay, so here I'll go through it more in more detail when we introduce this on Friday. But all these material here, and obviously we'll start. And from today onwards, as we record the session, I'll put the YouTube. There might be some delays, maybe 1 or 2 days delays, but we'll start putting them here, because we'll put them on the public domain YouTube, unlike Puneet, where you have to access it. Here we'll have the YouTube link, so you can just log onto this. I mean, you just access this page and click, and you should be able to see the videos. Okay, all right. Any questions on this GitHub page? And I'll show you on Friday how to pull this page to your Linux terminal. So you'll actually have this entire GitHub, what's called a repo, in your Linux as well. Okay. Any questions so far on the material or how to access this page or anything else? Okay. So then let's get started. Okay, so in the first session, what I'm going to do is I'm going to repeat some of the stuff which Puneet covered during his first lecture, but I'll give you a little bit more, uh, a simplistic view, like a custom view, and then in the end, I'll try to show you what are the similarities between what Puneet showed. They're pretty much the same, but I'll show from the custom IC design side some very simple steps of the whole design flow, and then take the entire complex digital design flow, which Puneet did, and show you that. But before I do that, I'll just do some quick, historical perspective and some, motivation on, what is VLSI all about. A lot of you already have an idea. Some of you don't. So I'll just give a little bit, what VLSI is about, where is it, I'll use a little bit of a historical perspective, not a whole lot of time, and then I'll just go through the design flow, some CMOS processing steps, quick CMOS processing steps. We'll cover it in detail in the second half to show you how, you go from a simple idea to actually a fabricated chip. Okay, so this is actually my brother's old brother's old cell phone, which I have it with me. So when we have these classes in real, I actually take this and float it around. I think this is probably like 2004 or 2003. It's a really old phone, but still gives you a lot of idea about, what's there. Like what Namrita from ST Micro was telling last Monday, everything, any electronic device you open, there's a chip to do something, right? The chips are everywhere. So I thought, cell phone is something pretty much everyone is used to. So I thought breaking open a cell phone and showing you some of the system stuff which goes in probably give you an idea what it is. Okay. So like I said, this is old phone, but everything applies till today. If you break the phone, it's just that there's more complexity and more stuff in than it was back, 15. This phone is probably 15 to, I don't know, maybe 17 years old, but essentially it's the same, but more powerful, more integration, more stuff. That's all. But essentially everything is in. So if you break open an older phone like this one, you'll see, so obviously at the heart of the chip is like, in most of your phone is probably going to have a Qualcomm Snapdragon, but it's probably not S1. It's whatever is the recent one. I don't know. This is a 1 core, 1 GHz. Right now, I think they're doing 16 cores. I don't know how many gigahertz, 3 probably. So it's more powerful than the desktop actually I'm using now. So that's how powerful these are. So at the heart of the phone is actually a processor. And obviously you have the memory. So right now, people are using, I don't know what, I think I still have 4 gig or 8 gig. People are probably using 16 gig memory. So this is also increasing day by day. So that's a chip as well. And typically all these phones have what's called a power management chip. And that power management chip is essentially because you have one battery. So typically it's a 5 volt or 12, some of them I think they're carrying 12-volt batteries right now, but most of them are 3, 5 in that range of voltage. So the lithium-ion battery. But all these chips have all different requirements. Like for example, this is probably running on 0.9 or 1.8 volts. This is probably running also on 0.8. So all the high power ones, high switching ones, they're running on really low voltages. Whereas the power amp, where's the power amp? Here. This is where it is communicating to your cell phone tower. This is high power, 1 to 2 watts power, or maybe even more. But this can't be low voltage. So typically this will require anywhere from 12 to 24 volts. So that's also supplied by this. And then, different chips have different requirements starting from 0.8, 3.3, 5 volts, 12 volts, and so on. So that's the job of this CMOS power. This is your radio. This whole thing is your radio chip. Um, so like I said, this is what's called your power amp. So all it has is just few very high power devices to actually convert all your voice and data into RF and send it through your antenna. So there is an antenna connected here I don't know if you can see the antenna connector is probably at the back side of this. So through the antenna, it connects to your cell phone, receives it as well. So this is what's called a transceiver. So you have both the receiver and the transmitter as well. And so usually there is a front end chip which does all the analog processing, and then this is usually the digital which does, because everything which goes in your cell phone, all the processing is in digital. All your signal processing, all your image processing, all that is done. I mean, not the image processing, but all your signal processing for your voice is done by this digital chip. These are, this is a mixed signal chip. This is mostly analog. This has primarily analog, some digital in it. Nowadays, obviously they have a single chip doing all this, but for most high performance devices, they're actually still a 3-chip solution or maybe 2-chip solution. Okay. And then obviously all of you use Wi-Fi's. So there is a Wi-Fi transceiver, just like your cell phone. There is a power amp, a baseband chip, and all that for your Wi-Fi. Then you have a CMOS camera, and these are obviously getting more and more powerful day by day. So that's also a chip, although this looks like a big one because there is a lens in it, but at the back of the lens is also a CMOS chip in it. The proximity sensor, so you probably noticed that when you take your phone and put it right next to your ear, the screen goes off because it knows that you put your phone right next to your devices. So that's a infrared proximity sensor. That's also a single chip CMOS chip with opto device in it. Your earphone obviously is another chip, but it's a MEMS device. Your microphone on this side is actually a chip as well. I'll show you an internal of one of this microphone. Headphone driver, speaker, obviously the speaker is a mechanical device, but the driver goes as a chip inside this, and so on. So you can see almost all functionalities, major functionalities in this phone or any electronic system is done through a integrated circuit. Okay. Now VLSI, which stands for very large scale integration, I just want to give you an idea on, how much is getting integrated into all this, right? Like this radio chip you're seeing, this is the old FM radio, which I grew up with actually, which I look like. This actually goes to like one tiny corner of the chip. These radios are way, way, way more powerful than, these are. The gyroscope, there is a gyroscope inside this, which, when you rotate the phone, for example, it knows that you have rotated. So there is what's called a gyroscope inside it. So actually, I'll show you a gyroscope which went into the first Apollo lunar module. I have a picture of it. But now it's a single, like a 1 millimeter by 1 millimeter or 3 millimeter by 3 millimeter chip. And again, I have a photograph of inside of a chip. I'll show you a gyroscope. So that's also a chip. This camera, I mean, I grew up with these, single lens and um, um, twin lens cameras. And the tiny cameras which you are, they're actually much more powerful than what, I use. Some of the optics are still good in this, but that's just because you can't, do something about the optics. It just needs the area. So that's the level of integration which has gone into this. The processor, like I said, even the PC I'm using right now is, your phone is probably more powerful to it. So, and, and this is just, so every year it is getting integrated. And I'll show you a Moore's law graph, which, Gordon Moore famously sort of prophesized in 1965. But, every year this is just getting smaller, more powerful, more device, and so on. So this is like a typical microphone. This is one of the popular microphones by a company called Knowles. And you can see this is actually what's called a micro electromechanical device. It's actually a chip, but it's actually got a mechanical device. Just a suspended diaphragm over here. So there is vacuum underneath this. So when you speak, this will um, uh, move this diaphragm, and the capacitance will change between these two electrodes. And then you have a IC which detects that change and that converts it into your voice. Okay. So this is a typical microphone. This is actually a larger size, but a smaller version of it is in your phone, which is, 2 chip. One is your electronic chip, one is your MEMS chip, which detects your voice and converts it into electrical signal. This is also another microphone. This is a kind of a newer microphone, piezoelectric based. This particular one is by a company called Vesper. Actually, I consulted for them. So you see a small, tiny chip here. that actually contains the, all the electronics. So the low noise amplifier is actually what I designed for the first version of this. So instead of capacitive, this is piezoelectric. So uh, so when you speak, there's a vacuum underneath it. I think I have a cross-section diagram here. Yes. So you have so this side is on top here. So so when you speak, the sound waves go and move these piezoelectric devices, and piezoelectric devices, as you know, they convert strain into voltage. So that strain is getting converted into voltage. So that voltage is converted by this integrated circuit into either analog voltage or digital. Most of them are digital, so they'll actually send you out. So there is an analog to digital converter here as well, and it'll send you out. So all your webcams, your cell phones, your laptops, wherever there's microphones, they're typically these microphones. Okay. Like I said, you have a gyroscope, like for example, when you rotate your phone, it does, but not only that, what that gyroscope in high-end phones it is used for is the navigation as well. So what happens is let's say you have the phone, you have it on your car, and you have your GPS signal on, you're going to a city, like let's say you're going to some city which has like really high-rise buildings, um, and tunnels and so on. And then once you get into the tunnel, what will happen is you'll lose the GPS signal, right? But you'll see most of these phones, especially the higher end ones, they still keep navigating. The reason is from that point onwards, they use this, what's called the inertial measurement unit, which is primarily a gyroscope, accelerometer, and a magnetometer, three things put in together. And what it does is just based on your rotation and your speed, it knows locally. But because of noise, you can't do that for long. And that's the challenge in building this. I mean, I've been consulting for a company for last 8 years or so to design one of these IMU units, and they still don't have a sample. They take a long time to get those noise really, really low. And so this is a gyroscope. I mean, this is probably a size of, I would say, like a bathtub, maybe. I mean, that's the size which was used, not a bathtub, but like a bathtub head, like maybe like 2 feet by 3 feet. I think that's probably the size. This is what went into the lunar module for the first moon landing in, I think it's 1969. I forget when it is, Apollo 11, I think. So and it was for navigation, right? When it was used, when they were landing, they wanted to know how far they were away from the surface of moon. So that's what they used. So this entire gigantic device is right now a chip. So this is an example. So ST Micro actually makes a MEMS gyroscope, triaxis gyroscope, and analog device and ST Micro are one of them. So you can see even in 2009, this was 7 millimeter by 4 millimeter, and they progressed slowly. And today they sell this inertial measurement unit, which is only 3 millimeter by 3 millimeter times height 1. So it's like few grains of rice. That's how small it is, right? So you went from this in 1969 to this in 2013, like in 50 years. That's what's happened to this technology. Well, 69, there were not, there's no VLSI, so it's not fair. But just to give you an idea, this is another gyroscope, which is what's called a BAW. And so it basically uh, detects your centrifugal force by detecting a curvature on a disc. So this is actually a disc, but this is a miniature disc. So you can see this is 500 micrometer from here to here. So this whole thing is about a millimeter by millimeter. So this whole thing is like a grain of rice, and it detects your angular momentum. Okay, and you put 3 of these in 3 axes, and then it can detect these. So like, for example, people who play those games like Wii or PlayStations, those also use these as well. Okay, and then you attach some electronics. So like, for example, I've been working with this company for, I don't know, 7-8 years now. I've designed pretty much all the TIAs. This is basically the low noise amplifiers. So there is a small RF transceiver unit which does some very complex signal processing to detect actually the angular momentum out of these what's called the MEMS devices over here. Okay, so this is also a tiny chip, like this whole thing plus a digital processor goes into a chip, which is, I think about 2.5 by 2.5 millimeter. It's in 130 nanometer technology. Okay. And like as I was saying, I know people kind of say this. I haven't seen exact numbers, um, but obviously it is true to a large extent. What's the exact number? Nobody knows. But like for example, a mainframe computer in the 70s filled an entire room like this, and obviously the core chip you have, which can fit in your thumbnail now, probably probably a couple of these fit on that now. Same thing. The entire command module in the lunar command module in 1960, yeah, so it's 1969 Apollo 11, which was used for moon landing. The entire thing or multiple of these can fit into this small size. So that's how advanced this field has become, and it's still doing it. Okay, so that's just um, very sort of a surfacial view of like where things are going, just to kind of, I think a lot of it probably you guys knew, most of it you don't. So I'll give a quick sort of a historical perspective of how this thing has advanced. Not a very detailed, I mean a lot of the books cover in detail, so you can go through it, but I'll just give you a quick overview of it. So like this graph is showing you the trend. So it's showing you the year. So this is basically the timeline and some of the industry trends which have driven this technology. And you see at the base, and you can see what's mainly driven this technology is actually computer chips, right? Because that's very ubiquitous in nature. It goes pretty much everywhere. So obviously people have wanted, somebody has a question. Sumanthi, you have a question? Okay. Um, yeah. So like as I said, the base of it is obviously the personal computers, the computing infrastructure, which has basically become mobiles now. The mobiles have become the computing, and then now obviously you have all this edge computing in IoT devices and so on. And if you look at the vertical is everything else, like starting from your multimedia applications to your wireless cellular data, speech recognitions, video on demand, biochips, IoT, automotive obviously is a big driver for this technology, but automotive moves at a very slow pace because of safety reason. Health is same thing. There's a lot of regulation involved. So they move at a much lower space, but they also drive some part of the technology. But the majority of this uh, integration is driven by computers, essentially. People wanting faster and more powerful computers pretty much every day. They want whatever you have today, they want twice as fast, twice as powerful as in tomorrow. Okay. Um, and you can see, it started with a single transistor in 1958. 60 went from actually less than one, which means that it was just a device. One gate in 60, about 64, around 64, you see getting to devices as high as 100. Then in the late 60s, it's about 100 to 1,000. And then in the mid 70s, you see about upper 20,000 when integration happens in that region. And in VLSI, when the term VLSI started getting coined around the late 70s or early 80s, we were talking more about 20,000 and more. And now it's called system on chip, is because now it's not integrating devices into the chip, but you're actually integrating systems. Like I showed you the cell phone, a lot of those systems like the wireless transceiver, the power amp, the computer, the memory, and this and all that is actually going into a single chip right now. So some high-end chips. And obviously in the processors right now, they're doing billion transistors in 1 millimeter square right now. Okay. And obviously the driving technology behind this is the feature size. So what is the minimum feature you can draw? right? So that's what has actually driven this entire industry, is when they're fabricating these devices. And later today in this lecture, and later today in the second half, I'll show you, some of the processing steps, and maybe you'll have a better appreciation of how, uh, you know, how these guys have just, just because, I remember in 2000 when I was just getting into this slowly into this industry, 99 industries, people were saying that 0.35 micron technology is the limit. People can't go beyond that. Before that, people were saying 1 micron. But these processing guys have continuously innovated and, kind of barsted through that barrier, broken that barrier on and on and on. And now we're talking about 2 nanometer, which is essentially, I think it's a stack of 1 or 2 atoms of silicon dioxide, and that's the kind of integration you're talking about. So it's just been phenomenal. So the heart of this is actually feature size. You can see it started with somewhere around 5 to 10 micrometer. Actually, before this, in 1965, it was 10 micrometer. So the smallest gate length or the smallest width of a metal you can actually fabricate was about 10, and now you're obviously down to 2 nanometer, 4 nanometer. So you're talking about scale of what is it? Uh, you know, 2 to 1 is 1,000. So it's 4 to 5 orders of magnitude is what they've gone in within this four decades, or four and a half decades. Okay. And obviously what has this resulted in is more number of transistors inside a chip. You can see in 70s it was in thousands, and now we are talking about, like in Pentiums it was 1 million, and now we are talking about 1 billion, right? In like the core titanium, the Intel or the AMD chips, you're talking about 1 billion. So these are the processor chips. But actually, where most of the integration happens and which takes the fastest advantage of the technology is actually the memory chips, because there's always more demand for memory than the processor in a certain period of time. Like especially now, people just want more and more memory because of everything is high bandwidth. So you can see the memory actually has been always a notch higher compared to the processors, right? So this is the famous Moore's law, which probably everyone must have heard about. So, um, um, and this is Gordon Moore famously in 1965. I think this was published in Electronics magazine, which was kind of lost. And there's an interesting story how Intel actually couldn't find an original copy, and they put a $10,000 prize, and some couple came, and that's how they find one copy of this. So that's how obscure it was. Till after 10 or 20 years, people really saw that it was really following. I mean, in 75, they made an adjustment. So what Gordon Moore saw was, like you can see, he published this in 65. So starting from 1959 to 65, what he saw was that every year, the number of transistors going in the same chip area was doubling. So, um, so this was every year. But okay, so this was till 65. Number of
All the caps here.
you guys need to mute yourself. 1 second, I want to just mute everyone here. Okay, so yeah, so number of transistors in a given area was doubling, right? Was doubling, so 2x every year, every year. So that's what he saw. And, it kind of followed like that till 75, but in 75, they kind of did a, or didn't do it in 75, they retracted it back after seeing the data. It was more like 2x transistors every 2 to 3 years, or every 2 years is what usually they say, okay? And it has followed since now. So, every year people make thousands of predictions. Obviously, this will be this, number of IoT devices will be this, that, and all that. This is one prediction which has actually been true till now, which is amazing. And obviously Gordon Moore himself was a genius. So this is another trend, just showing you, how the power and voltages are scaling. So for example, you can see around 2004, the currents required was scaling much faster than the voltages were scaling down. So you'll see later on during the course, like some of you probably already know, especially for digital, actually, it's purely dependent on the voltage. So if you're lowering the voltage by half, your power will scale by the square of that. In analog, it's a little different. It's dependent both on voltage as well as current, because you can control both. But in digital, it's pretty much the voltage because it's half CV square. Okay. But obviously, towards um, maybe around after 2006, you can see it's flattening a little bit, but now it's actually growing back again. So actually, the biggest challenge for processors now is actually heat. It's not that the technology is not allowing them to cram more transistors. They just don't know how to dissipate that heat. Like if you open any of your laptops or your desktops or your graphics cards, you'll see there's like huge fans, huge heat sinks, because the power is a big problem. You take like 100-watt processors, and typically they're about 85%, 70% efficient. And so you have like 20, 25 a watt. It's like having 4 LED bulbs inside your small laptop burning all the time. I mean, that's how the heat is. Okay. All right. So that's a quick overview. I wanted to give like the historical perspective, plus how the industry is kind of progress throughout the year. Any questions so far? I think it's more of just very rough info. But if you have any questions, feel free to ask right now. Okay, so next what I'm going to show you guys is it's what's I called is a custom IC design flow. What Puneet showed you is actually what most people use in a very complicated digital circuit, and I guess it comes from some background, right? Puneet has worked mostly in companies where they're doing all these big processors, so that's the one they use for. But I thought I'll introduce you to how people do just pure custom, like analog design, pure custom digital design, and then show you where the differences are, and so that way hopefully you'll get a clearer idea on the steps. And as we go and introduce more CMOS processing and go throughout the course, I think you'll have a better idea on how to integrate those design flows in. Okay. So the example I'm going to take right now is if you're doing a very simple, let's say analog chip, right? So it starts obviously with some idea or a specification. So if you're in a small company, usually a marketing guy will come and give you a specification saying that, hey, I want this chip. These are the specs I want. If you do this chip with this spec, with this much area, this much cost, I can sell it with this much profit. And, that's how they come with the proposal. Obviously, it never works out that way. But that's how it starts. Okay. So as designers, if it's a simple chip, it's usually one designer or two designer or three designer. They're the ones who are architecting. So they will come up with some architecture, and the architecture is a place where it is mostly technology independent, but in analog, pretty much everything is technology dependent. You have to choose a certain technology. Like you'll say, okay, I want to go with 130 nanometer TSMC or a 350 nanometer IBM process or something, because it's so tied together. And I'll show you in digital, they don't care about a technology till they get to synthesis. Okay, but in analog, they're so tied together that typically, but in typical architecture, you come up with an architecture where it is technologically independent. So if this was a baseband chip, you're going to come up with an architecture saying, okay, I'm going to have a complex mixer with I and Q, power amplifier, and two LNAs with the image reject filter and blah, 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 and so on, right? So, and you just come with some very rough estimate of the cost or performance. And typically you'll probably simulate this in a high level language environment, like for example, um, MATLAB or Simulink or Verilog A or System Verilog or something like that, and simulate this to make sure you can meet the spec your marketing guy is asking. and just do some rough cost estimates. Okay, if you don't meet it, you go back right to your marketing guy and says this is too difficult, it'll cost us a lot more money to build this and will not make profit. So they might make some changes, or they say, okay, this for this market we'll do this, and so on. And then you kind of go through this loop till you get satisfied. After that, you do circuit design. Like I said, if you're doing custom circuit design, if I was designing LNA as a circuit designer, I would just start putting. And this is technology dependent in the sense that I need to know what technology I am designing it. I just can't go say, okay, I'm just going to do a two-stage, I mean, a source follower LNA with this inductor values and so on, because every technology has different performance transistors, different ways you can make inductors or you can make inductors and so on. So I have to choose a technology in full custom analog design. And same feedback loop. So for example, in this architecture, let's say this LNA stands for a low noise amplifier. So based on this architecture, so there will be some specifications which will come out of this low noise amplifier, and that'll be given to the circuit designer. Okay, and the same feedback loop goes here as well. So they'll give you some numbers. They'll say, like, for example, here there's some numbers. There's a gain of 25 dB, linearity of plus minus 1 dB, and ACPR of minus 40 dBc, and so on. You don't have to know what those means, but some specs. And then you design and you say, no, there's no way in this technology I can do it. Either you change the technology or you go back to the architecture and the marketing guys and say, this is going to cost you too much. If I make this change, then it's doable, and so on. So, and you go through this conversation again till you're satisfied. And then once you get satisfied, and obviously you'll be running simulations to make sure of this. And these are circuit level simulations like SPICE or Spectre or Aldo. These are simulators from different companies. You do that, verify, and then this is an abstraction in the sense that um, when you're going to send your circuit for fabrication to the fabrication house, let it be TSMC or Global Foundry or IBM or whatever those foundry houses are, you can't send them these. Okay, they don't know what to do with this. You have to send them this sets of polygons. Basically, you're drawing them every physical structure which they need to fabricate. Okay, I mean, it's done all automatically, but you have to, and this is what's called the layout. Okay, so from this circuit design, you use what's called a PDK. So the process design kit provided you by the foundry house, and essentially there will be ways to draw this transistors, inductors, and so on. So you use this process design kit using obviously CAD tools like Magic or Virtuoso Excel, or Tanner Edit, or whatever tool you are using, and create these figures. Okay, specific figures based on the rules the foundry house gives you. So that's why I told you that you have to know a technology when you start designing this, because it's very closely related to what you're designing. Once you do this, um, and again, this after you do this, what you do is what's called post layout simulation. So there are a lot of things which are not available to you in this circuit, and they're usually what's called parasitic. Like from every node to another node, there is a parasitic capacitance, which is not captured here because you don't know how you're laying out, because there are a million ways I can lay out these two transistors, and I'll have a million different combinations of parasitic um, um, capacitance, and most of them will make my circuit completely dead, and some of them will not. So that's where you have to extract using tools, find out what those extra parasitic capacitances and resistances and all those diodes have come into picture. And then you go back and simulate again to make sure that you still meet the specification. If you don't, then you go back through the loop again. Okay, and then once you're happy, you send this mask. So these layouts with these figures, they convert these polygons, they get converted into physical masks. Okay, and I'll when I show the processing step, it will be a little bit more clear. You send it to fabrication, and those guys, they will take one wafer, like a 6-inch or 8-inch or a 12-inch, the circular, what's called a wafer, and fabricate thousands chips or 100 chips, like an Intel titanium processor. They'll probably only be able to do 10 or 12 because those chips are huge. Whereas like accelerometers I was showing you, some of them 0.3 millimeters square. So you can fabricate about 100,000 to 500,000 devices in one wafer. Okay, and they will cut and dice it and send you those tiny squares of 100, and you take them, you package them, put them inside packages, and that's the typical ICs you see in your circuit boards, which you have done. So because this itself is useless, because there is no way to send data in or read data in, because these things are small. So you see these tiny little squares here, they're called what's called pads, IO pads, and they're about 100 micrometer by 100 micrometer. So they're very small. So you have to attach small lead wires. I'll show you some figures which will be more clear. Actually, there was one figure in the microphone which maybe I'll go back. Okay, so there's a question here. How simulation is different from post-layout simulation? After doing the layout, we connect these parasitics and then we do the simulation again. You don't, I know pre-layout, but always confused about post-layout. Okay, I think it'll slowly be clear once you start doing the exercises in layout, but you don't put parasitics. It's called parasitic for a reason. It's parasitic because you don't want it, right? It's like that's why it's called parasitics, like a parasite, right? Parasite is something you don't want in your body. The same thing here. Parasitic is something you don't want it, but you can't avoid it because that's part of the technology. When you draw two wires, you're going to get capacitance in between them because you have two metals, you have a dielectric in between. That's just physics, right? Why don't you capture in here? Like as I said, you just don't know till you lay it out, right? You have a model for this transistor which will tell you in isolation what the model is, and that's what you're simulating. You have IV characteristics of this. You have the drain current versus gate for drain current versus drain to source and so on, assuming this is in isolation and there's nothing connected, there is nothing beside it and so on. But that's not reality. In reality, you have lots of transistor in between it, you have interconnection and all that, and that they cannot put in the model because they have no idea how you're going to lay it out, because that layout is going to vary, like as I said, in 100 million different ways. And that's only after you lay out, you use tools which actually calculates these numbers. And later, not today, tomorrow, when we introduce passive devices, it'll be much clearer then. I'll maybe come back to this point again. But basically, you do post layout sim because there are a lot of resistances and capacitance which get introduced after the layout, which was not part of your original design here. And most of the time they'll kill your circuit. If your circuit is very high performance and you didn't do a good job of this layout, it'll come back and it'll not work. I mean, come back in the sense when you do the post layout, it'll not work. And in analog, a lot of it is you can't even capture in post layout. As a designer, you just have to be aware of it from your experience, right? So I have these like 1,000 different thumb rules I use when I'm doing layout or circuit design, that because those things don't get captured by the layout. Why? Because they're just too complex. And so that's why a lot of people, go away. Like in universities, you see most professors will just go away from analog design because they will do this simulated and everything is working fine and dandy. And when they get the chip back, it's just completely dead. It's not like they're not meeting the performance by 10% or 20%, but it's actually completely dead. And that just takes a lot of years of experience for you to know, like, I should not do this because if I do this, the simulation is still going to show okay, but I know it's not going to come back and work. Maybe I'll highlight some of these while we are doing our lab exercises. Okay, like as I said, just pay attention to as we go along. It'll get more and more clearer, and as you're doing exercises, it'll be more clear. Okay, how do we get from here to a chip which we solder on our PCBs and get all these fancy devices, right? So you go from this abstract idea where you say, I want to design this where I take a voltage in, I take a voltage out, small voltage in, large voltage out, and ultimately ends up with this like really tiny millimeter by millimeter chip which gets packaged into this, and then you put this in PCB and put it in your phone and it works, right? How does it get converted? So I've taken an example. So I'll quickly show you example of an inverter, and I'll repeat this many times today. So just have patience, because the processing step when somebody is getting introduced to it first time, it's a little bit confusing. So don't worry about it. So, you know, I'll keep repeating it a while. So essentially what happens is you draw this and you simulate it in your simulator, your SPICE simulator. So for example, here it's an inverter. You have a PMOS, you have an NMOS and some parasitic caps here, or a real cap here, and you simulate this. But this is an abstract, right? It's just a mathematical model. This three-terminal device, you can draw it any way which you can. Like for example, like I keep saying, you can put your face here, put three terminals, and if it's the same model, it will give you the same result. You put a smiley face, you put a sad face, you know, you put anything here, as long as the mathematical model is defined between these three terminals, actually four terminals, there's a bulk here too, then, you know, you'll see the same thing, but it's just a mathematical model, right? So, but when you send it, like as I said, you send this to the foundry house to fabricate it, they'll send you back. They'll say, what is this? I don't understand what this is. Because all they understand is those layouts, which gets converted to this. So this I'm showing you how um, like a two transistors finally after get fabrication. And this is a cross section. So this is actually, you know, if I draw the 3D, it's, you know, it's kind of, so you basically have so this is, you know, wafer which is cut right in the middle, and I'm showing you the cross section. So this is basically your height or your y direction. Okay. So how do we get from this you know, abstraction to this layout? Okay. So the key in IC design process, and this entire industry which has gone through this phenomenal uh, you know, phase of just integration on and on, like the Moore's law, and you've gone from a lunar module of this like size of this house to sitting on your thumbnail, is really on the processing step, the material patterning which they do. And that's what they have continuously have innovated on and on and on, and broken all kinds of barriers to where it is right now. And, you know, they're obviously, they'll just keep going. I don't see them stopping. So I'll just quickly introduce you to the patterning steps. And, you know, some of these may seem like, um, you know, initially you might be feeling like, okay, I don't understand it. But so just like I said, have patience, but try to understand it, because the processing steps are very key to, especially if you're going on the backend side. If you're just doing Verilog programming, and you still, it's always good to have a good idea. But if you're anything in the design or the verification or the P&R or any side, knowing the process steps is very key. So just, you know, try to pay attention and try to observe as much as you can. So here, for example, we have what's called a wafer. So again, this is a cross section. So if I draw the, so this is a block. Basically, this is a block, right? I mean, it's a giant wafer. It's actually circular in shape, but I'm just showing you that this is a cross section. So let's say so this is usually what it's a silicon substrate, right? And let's say you want to pattern this material, and let's say this material is, let's say metal, let's say aluminum, right? So you want to pattern it, because that's how you want to route, right? So you basically don't want this entire block of aluminum. It's no good. It's just a sheet of metal. You actually want to pattern it in some fashion. You want to route it, right? You just want to do some patterning like this, right? So you want to do something like that. So how do you go about doing this? So the first thing you do is, and this process is what's called a photolithographic process. It comes from actually photography. You guys are in a generation who probably doesn't know what that photography means, but I grew up and I actually did a lot of my own photos, developing my photos. So it's the same process. What you do is you take the substrate, you apply the material. So let's say in this case, this was aluminum, and you apply what's called photoresist. So you basically put a thin layer of photoresist on top of the entire substrate. And you take this mask, and these masks were generated from your layout, right? The layout which you saw, the, you know, the squares, bunch of squares, and, you know, doing connection. You did all that. You send it to the foundry house. That's what the foundry house did. The foundry house actually converted them to mass. And the mass is nothing but this is glass, and this is some opaque material. So wherever you have drawn your squares, they either open it or they closed it, depending it's a negative process or a positive process. What it means is that, do you want that pattern to be done in that block square, or you want it to be removed? Depending on that, they do a negative mass or a positive mass. Okay. So here, for example, it's a glass, and you do some chrome pattern on it, which is opaque, and you shine UV light. When you shine UV light, the places where the photoresist shines, that becomes soluble in some chemical. And so after you shine it, you pass it through that chemical, then what happens is it just makes everything soluble in under this. These things get hardened wherever it is. And like I said, depending on the process, if it is a negative process, it will be the opposite. And then you basically remove that layer. And then once you remove that layer, you remove the photoresist after that, and what you remain is these patterned materials. So now you have those the patterned materials basically, right? So this, and you can use them for routing or doing your gates or whatever you want to do. Okay, so that's the basic process on how you do it. Okay, so that's the patterning process. So now we go from um, this devices. So you can see each PMOS is this layout. So basically this is your gate, like this is your gate here, this area over here, this is your source, drain, then you have this, sorry, yeah, this source drain, and you have this drain connection to VDD from one metal level to another metal level, because there are stacks of metals, and I'll show you maybe in another slide. And same thing, you have a NMOS, which also has a gate area, source, drain. They're all drawn through these sets of polygons, basically. Okay. Now, what do they do with these polygons? So once you send these layouts, these layouts are what's called in layers, right? So there are different layers. So depending on the complexity of the process, so you could have some simple processes even today, which are only about like 10 to 15 layers. And then you have the Intel processor, which I don't know how many layers. There are probably 250 to 300 layers. So what it means is that each layer will actually go and fabricate a certain part of the device. Now, one thing I want to make clear is this is what's called a monolithic process, right? So in monolithic process, so when you do like a system PCB design, right, what do you do? Let's say your PCB has 4 ICs, has a processor, one CMOS chip, couple of resistors, capacitors, and all that. You actually pick one of them. They're off the shelf. You pick one of them, place them, and solder it and wire it and so on, right? This is what's called a monolithic process. You don't pick devices one by one. You don't pick the NMOS first and fabricate it. You don't pick the PMOS. You you actually develop all portions of every devices at once. In the sense, all the NVELs of all devices will be done at once. All the PVELs of the NVEL devices at once. All the gates of all the devices will be done, because these are planar. Once you're done with that layer, that's it. It's done. You go to the next layer and so on. Okay. So here I'm showing that you just have one inverter, and you had a P well and a N well, and basically it's a well with a certain doping, and you drew a mask, right? So this is what you drew in the layout. So this was your layout, right? This was your layout. And sometimes you don't even realize you drew this, because you use what's called a P cell. You just use abstract, you place it in, which has hundreds of layers, or not hundreds, but tens of layers inside it. But the foundry will segment out only the layers for each particular processing step. For example, here it's doing the P well and well. So it'll pick your P well. This is your P well layout. This is your N well layout layer. It'll pick those. And when I say pick those, that means it'll take the mask, which has these, and create this. So using the same photolithographic process, it'll actually create these two N wells, and it'll do this isolation. So this is silicon dioxide here. It'll isolate those two devices using silicon dioxide. So this is what's called a STI process. So it isolates between two and today, later in the afternoon, I'll explain a little bit about these processing steps, how to isolate and so on. Okay. And then it takes the same mask, which it did before, and it will lay the gate oxide. The thin gate lead oxide is using the same layer of mask. It actually does the gate oxide using the same patterning steps. Then it takes the polygon from your next, from your layout, it takes the next mask, which is your polygon, polysilicon, usually. It'll take this mask and it'll make the polysilicon gates using the same patterning steps before. And then using the same mass, it'll actually do what's called the source drain implants. Okay. And this is what's called self-aligned. I'll explain more later on. Self-aligned implant. And if you ask me what is one critical processing step which is enabled is Moore's law, I would say it is this. Okay. Because these gate lengths are, like I said, they're now 2 nanometer. There's nothing, and even when they were 1 micrometer, when they were 180 nanometer or 180 nanometer, there's no way you can place them with absolute accuracy within few angstroms of it. No process will be able to do that. And if you can't do that, these devices are waste. They will not. Even a slight misalignment it'll be waste. Okay. So this self-alignment process, which assures that the source and drain, they start and stop exactly where the gate ends. Okay. And that's probably one critical step which decides this, what do you call it, this whole Moore's law, because without that, it would have been really, really tough. I won't go into the detail, but the whole idea is, I think you get the idea. So they just keep taking different layers and they keep doing different steps. Like, so now what they'll do is once the gate and everything is done, they will isolate all these layers using silicon dioxide. Mostly in CMOS, it's purely silicon dioxide because of processing reasons. If you're doing power amplifier in gallium arsenide or gallium nitride, then this is silicon nitride. So they'll use this insulating layer, and then after that they will, so let's say you have to connect to the source and drain. So they'll punch the holes, for example, fill tungsten here, and then they will do patterning of your metal layers. So they'll connect the metal layers. So like, for example, this was your NMOS, and this was your PMOS. This was your source of your NMOS. This was your source of your PMOS. This was your drain. This was your drain. And essentially, you're connecting the sources together. Your drains, you're going to take it to VDD, this to ground, and so on, just based on your layout, right? And ultimately, when it is done, this is what you're going to get, like something similar to this, where you have your 2 transistors, you have your gate connected together, you have your drain sources connected together using this metal layer, and then you have your drains connected to VDD with another metal layer, and so on. Okay, and this is what I showed you here. It's called a STI process, the silicon trench isolation. This is called a locus process. I'll explain more today in the second half. But this will essentially this was used in the older process to isolate devices. I'll explain a little bit more. But as the gate sizes and the feature sizes got smaller and smaller and smaller and smaller, it was difficult to use this process. So then they started using what's called STI process. Okay, the shallow trench isolation. Actually, before I go on, any questions on these steps so far? Okay. Okay. Everyone, just put a thumbs up if you are following it. At least half of it. I mean, I know some of it may not be. Just do a thumbs up, so I know that you guys are at least barely following it. Like I said, I'll repeat it a couple of times. So nobody understands it so far? Just one thumbs up. Okay, yes, sir. Okay, so Sumant, you said these are all between 1 CMOS. I don't exactly get the question. You can raise your hand. I can unmute you.
Sir,
Yep.
you explained all these. These are all the functioning of only one CMOS or multiple CMOS?
What do you mean by one CMOS?
No, means this is the structure of only one CMOS or a combination of many CMOS?
You mean one CMOS device or combination of
Yes.
CMOS?
Yeah.
No, no. So, like as I said, now they are putting 1 billion transistors in 1 millimeter square, right?
Yes.
And you have, for example, a 88 inch. Okay, maybe I'll give you this. Maybe that'll wake you guys up. Let me give you this, right? Okay. So I told you, right? This is, so they take a wafer. So for example, processors, most popular is the 8-inch wafer. And 8-inch is how many centimeter? I think it's 20 centimeter, right? Which is
Yes.
200 millimeter, right? Roughly. This is the diameter, right? And if my chip size is, let's say, 1 millimeter square, so it's 1 millimeter by 1 millimeter. Okay, so basically it's more complex. They have scribe lines and all that, but let's just keep it simple. So they're going to cut all these. So I showed you only 2 transistors, right? So how many 1 millimeter, how many of these devices will come out of these wafer, 8-inch wafer? How many chips? Okay, so calculate. Let me see who gets the answer first. So okay, 31,415, 200. Okay, let's see how many of you get it right. I mean, see, okay, maybe here I'll digress a little bit on, doing sanity checks. That's what makes you engineers. Okay, nobody else? What's happening? Everyone just like taken off, sleeping? It's all boring. Okay, just raise your hand if you're actually watching this video. Can you just raise your hand? Okay, still like half. Okay, so did you guys follow at all? Like so do you understand what the question is? Like, can you ask me if you're not understanding what the question is? So like as I said, I'll show you again during the processing step, but these chips are manufactured on a disc shape of 8-inch square, right? And each chip is not 8-inch, right? Each chip is very small. So I gave you a problem where I said you have, just give me a second here. So I gave you a problem where I said you have an 8-inch wafer and you've designed a chip which is 1 millimeter by 1 millimeter. So you send this to the fabrication house, they use the 8-inch wafer and they fabricate it. How many chips are you going to get? Around 6,000, 31,200, one get 31,000, 31,415. Okay. All right. Okay. So here I'll probably maybe digress a little bit. When you get answer 60,000 approximately. Okay. So this is saying 60,000 approximately. All right. Okay. 31,000 approximately. Okay, good. Yeah, I want just approximate answers. Okay, so I get wildly varying answers, right? So I got 31. So most of them are in the 31,000. So maybe some of you are thinking maybe that's the correct answer. But how do you do a quick sanity check? Okay. And I keep saying this a lot, that for engineers, your sanity check is your bane of your existence, in the sense that when you're designing or doing anything, there are a lot of things you just have to quickly check um, um, by hand. And because some of them, otherwise it'll be a months around turnaround time before you realize that you have made a mistake, right? So you want to do this quick sanity check. So there are various ways you can do this problem, but one way I would do is, you can say this is, I'll assume that it is a 8-inch square, right? If it is a 8-inch square, then it is what, 200 millimeter by 200 millimeter. Now if I have, how many 1 millimeters I have on each side? 200. How many 1 millimeters on this side? 200. So 200 times 200 is what? 40,000, right? But obviously, these areas, there are no chips here, and that's your pi factor. And that's roughly about 75%, let's say. And so then that this is roughly around 30,000, right? So people who got answer 200 or 60,000 or 3,000 or 6,000, you should quickly hand check it and say, okay, that doesn't make sense. I made a calculation error somewhere. Okay. All right. So right now, in a 1 millimeter square, they're cramming in 1 billion devices, right? Sometimes you can't get 1 billion devices routed. There might be only a few 100,000, but logically, technically speaking, you can cram in 1 billion devices. So in a wafer, you can cram in 30,000 times. So basically, what is it? 30 trillion devices in this wafer, right? 30 trillion devices in this wafer. So the steps I showed you, by the end of it, so if let's say this was inverter I was doing, and I was doing 15 trillion inverters with 2 transistors each, all the 15 trillion inverters are fabricated by the end of this process. You got it, right? So it's not like 2 are done, then the next 2 are done, and so on. For each wafer, actually these are bunch of wafers. So they put in, let's say, 12 wafers. All 12 wafers or 14 wafers or 100 wafers, all the 30 trillion devices will be fabricated at once. Okay, so when the steps are done, you have the entire 30 trillion devices done. Okay, so did that answer your question, Sumant? And everyone else?
Yes, sir.
Okay, good. All right. Any more questions? Any just makes sense? Like I said, we will repeat it a couple of times, but I want to make sure at least you guys, understanding the basic concept of it, not like, completely lost. Okay. All right. So now I will go through the design flow, and this time I'll go through a IC design flow, which is pretty much what Puneet showed, but just the simple steps, which I think Puneet covered, and then he expanded. And maybe, not maybe, on the last slide, actually, I'll show you one-to-one, what I'm saying and what Puneet was saying. So that way, there is no confusion in, later on, if you're watching the video and you go like, oh, why is this, formal verification here and functional verification there, and so on. Okay. So in the digital, obviously, the first step is SEM. You have an idea or some specification is given to you. So for example, here I've taken an example where somebody is trying to do a SPI chip. Now, in present day, that seems too simple a chip to do, but 20 years ago, that was a complex chip. Maybe not 20 years ago, but maybe 3 decades ago, that was a complex chip. So let's say you want to do a SPI protocol. So the SPI is basically a communication. It's a serial communication protocol. And for example, in a lot of the IoT devices in present days, they use that. And if you, so as a designer or a architecture guy, you are given some data sheet, like this is the protocol. This is what, so for example, in case of protocols, usually a body, right? A IEEE standard body or some body will decide, like for example, Wi-Fi, right? Wi-Fi is IEEE protocol. defined protocol. So there is a body in IEEE which defines those protocol. So in this case, the protocol doesn't come from a marketing guy, but what the marketing guy will come and say is that, oh, there is this protocol. If we design this chip in 3 months using so many resources, blah, blah, and all that, we can make money because there's a demand for it. So that's what he'll come up with. Okay. So, so you take the protocol and, this protocol usually will have, 10 pages of documents or 300 pages of documents. Some protocol would be 30,000 pages of document. You take all these documents, timing diagrams, and definitions of the protocols, and you come up with the architecture. So here also I haven't shown the architectural phase, but the RTL design is, I kind of take it as part of the architecture design. So here I've taken a simple um, um, block where I say, okay, I'm doing RTL design and I've shown how it will look in Verilog. So this is basically Verilog. Uh, Verilog. And so it's defined in a language, right? So it's what's called a behavioral model. And this is this is not technology dependent, right? So like, for example, I was saying when you're doing custom analog design, you need to know what technology you are designing in, because without that, there will be a lot of unanswered questions, even though you're in an architecture position. In most digital design, you don't need to know what technology you are in or you're going to go in. That decision can be made later on. So you can do your behavioral and your functional design in Verilog without knowing what technology you're going to go in. For example, this is what's called a behavioral design or RTL design. So the RTL design is usually written in a HDL language like Verilog or VHDL, or people even write it in, like System C and so on. Okay, so that's your design phase. So this is where you take the previous specifications and you convert that into what I call is the functional module. Okay, or the model for it. And once you have this, you're going to simulate it. And here, I've shown, like, for example, you have this design of your SPI and you simulate it using any of the simulators. For example, you guys use EDA Playground. In EDA Playground, you can use any of the Verilog simulators like Incisive or the open source tools. And this is purely behavioral in nature, and these are what's called event driven simulation. So they just understand events of zeros and ones at a particular time step. That's all. So these simulators are called event driven simulators, unlike SPICE, which actually solves your entire equation, your models, your everything to basically solve currents and node equations in your circuits, right? So here they don't care about your circuit or anything. It's just saying that at this point there is an event, this node goes from 0 to 1, this node goes from 1 to 0 at certain time steps, a certain time delay, and so on, right? So it's purely a event driven simulation. So there is no technology involved at this point. And so essentially you do the verification of your design. So whatever you have designed, looking at um, um, the spec sheet and um, your protocol and definition and so on, you do that and you verify using these simulators. And this part, usually in this industry, it's called front-end design. Okay, so when people are saying, oh, we're looking for some front-end VLSI designer, they're essentially looking for RTL designers or verification. And you'll hear a lot of word called DV. We're looking for people with DV experience or people who can do DV. That means design verification. So essentially, the job is somebody has written thousands of lines of codes of Verilog, and there is a separate team which sits and verifies it. So designers usually don't. This is for really complex chips and big chips. For small chips, obviously, it's one guy doing everything. Like most of the companies I was involved in, it's one guy doing the processor, the RTL, the verification, place and route, the whole process, right? So they're simpler chips. So you do design verification, and just like in the custom steps, you basically make sure that your design meets the specification. If it doesn't, you change your RTL code, your VHDL or Verilog code, to make sure you meet that specification. So as long as you don't meet it, you kind of go through it, right? Once you're verified and you say, yes, we are good, that's when you go to synthesis. Now, synthesis, once you get to the synthesis, that's where you are technology dependent, right? Technology dependent in the sense, right? So before this, it's just purely behavioral, right? Like as I said, it doesn't know you're going to fabricate this in TSMC 130 nanometer, 65 nanometer, 4 nanometer, 2 nanometer. It just doesn't know. It's just saying that behaviorally it is working. Now you can typically what people will do is put delays and all that in the RTL code to kind of mimic some of it, but most of it is just pure behavioral simulation. Okay. But once you get to the synthesis part, so synthesis is basically taking this behavioral model, which has no idea of the circuit, creating actually a circuit, right? And this circuit, these gates, and these are usually called standard cells. Okay. Standard cells are essentially NAND gates, NOR gates, OR gates, AND gates, and D flip-flops, RS flip-flops, tri-state buffers, and all that, right? The standard uh, series of gates which are called standard cells of a particular technology. So when you want to use a certain technology, let's say I want to use XFAB 0.6 micron technology. So first thing I do is I download what's called the PDK, process design kit, like I was saying. And these cells are part of that process design kit. It will tell you what are the standard cells. And, we'll cover something as a great presentation on standard cells. So he'll cover in detail next week. And you're going to lay out one standard cell, like the first inverter, you lay it out as a standard cell. So this PDK will have hundreds of these standard cells, different varieties, different fan outs, different driving loads, basically depending on where it is going to go, like in a circuit. If it is driving a big capacitor, there will be a standard cell with big driving capacity. If it is driving a very small load, then it takes the minimum sized driver to drive it, and so on. So there are all these variety of standard cells with different flavors of them. So you'll see most of the standard cells will call 1x, 2x, 3x, 4x. Basically tells you how big a capacitor it can drive. Okay, so you need to know what technology, and that this is where the tools will use your PDK libraries. A code for a shift register like a SPI. It most probably, I mean, this is actually custom drawn. It'll probably not draw it like this. It'll be just a big wiring mess with all this, but functionally it will be just this. It'll be a shift register with some ANDed clock gated logic and so on. Okay. Any questions so far? Everyone understands what a front end design is? And like I said, I'll show the differences or the similarities between what Puneet had shown. Puneet actually showed the same thing, just some nomenclatures were slightly different and so on. Okay, who understands so far? Just raise your hand. I think this is pretty. Okay, all of you raise your hand who understands. Okay, those who haven't raised your hand, it's just like you understand or okay, looks like most of you. Okay, good. I hope you're not raising the hand for the sake of it. I think some of you are probably doing that. Okay, good. So this is called this is moving from the front end process to the back end. And like I said, once you get to the back end, then you need to know what technology you are with. From there on, you can't say, I want to be still technology dependent, right? And here also, you still do gate level simulation. So you might ask the same question like what Sumant asked, like, why are we doing this? Because this process from RTL to synthesis it's actually not a one-to-one process. If it is a simpler design like this, it is pretty much one-to-one. But if it is a complex design, because essentially it's algorithm, right? So it depends on how good the algorithm is. Sometimes the algorithm might say that I have generated what you wrote in your RTL, but may not be it is. So that's why you have to do the verification of the worth of real time. That's how computationally sensitive is. Because once you get to the gate level, now you have to um, use actually the transistor level. Now, most simulators will not use like spice level. That's just too slow. They will usually have what's called fast spice or table models and all that, which is kind of in between spice and behavioral models. So they will, for example, they will just take the MOS and model it as a switch. So your improvement in simulation time will be like orders of magnitude once you do that. So that gate level simulation is done that. So after this is simulated, they actually simulate. So whatever verification you did at the RTL level, they'll take the same test benches and do those simulations for this gate level, because they want to make sure that whatever RTL code you wrote, you're able to the generated netlist is actually that same design. It's not like something else. Okay, because somebody has a question. Okay, no. So that's the purpose of actually doing this gate level simulation. So it's basically verifying that whatever behavioral design I did and whatever has been synthesized to this gate level netlist is actually one-to-one. So you do this gate level simulation or formal verification. Formal verification is basically a mathematical tool which will take your gate level and it will take your behavioral level and it will say, yes, 99% probability that these two are similar in nature. Gate level simulation is 100%. If your gate level is agreeing with your simulation, then you're 100% correct. But whereas with formal verification, there's still a probability of it. But for large designs, that's usually is a crucial step, because gate level simulation will take you days to do it. Okay. And if you're happy, then you go to the physical design process. Okay. So just make sure you guys understand, in custom design, when I was doing design from here to here, from circuit design to layout, it's all manual. There is no automation there. So if I have designed an amplifier, I pretty much design the entire layout by hand, in the sense I have to place the device, route them, hand in the sense using the CAD tools to do it. Whereas the process from going from the behavioral to synthesis and synthesis to physical design is all automated in semi-custom flow. Now, in full custom flow, like the chip we designed here, for example, in silicon, we did SRAM with decoders and all that, with a SPI and all that. That was actually a full custom digital design, in the sense that we use standard cells, but all the routings and placements and all that was done by hand. It was a small design, and it was for undergraduate students like you, and I wanted them to get a full custom experience. So we did that whole thing. So the whole thing was actually laid out by hand. There was no automated tool use. And same thing, we didn't go from Verilog to gate level. We straight went to gate level. So for example, people were given like SPI, right? So I gave one group to do the SPI. Like you remember on the first day, Prachi came in, and so she and another girl, Suruchi, they did the SPI. So I gave them the IDEA protocol. They straight designed the gate level using the standard cells. Okay, using the standard cells, they straight um, uh, designed this actually. Actually, this particular circuit is from from their schematic actually. So they actually designed it like you would do, like putting a shift resistor and all that. So that's a full custom design where you don't use Verilog at all. Some people, even in full custom, they use Verilog and synthesize it. A lot of times, if the digital block is small enough, then you just design it by hand. And in the sense, the classical, you don't do RTL and synthesis. And then layout, same thing. You just take all these devices, standard cells, and you put them together by hand, and you route them by hand and do it. But obviously, for processors and all these complex digital systems, you can't do that. So you are going to use automated tools to do this. Okay. So the physical design process is taking this gate level, and like as I said, in the custom design process, the circuit design has mathematical models behind it, right? So you have transistors inside this or behavioral models of flip-flops inside this, which tells you how the circuit behaves given certain voltages at the inputs or currents at the inputs or events at the inputs, right? It does not know anything about the physical device yet, right? So same thing, if I take this circuit and I send it to the foundry house, they will not know what to do with it. They'll might know like, oh, this looks like a circuit, but they'll not know what to do it. For the foundry house, this is what they need. So this is actually a layout of a single flip-flop. So this is a single flip-flops layout. So you can do a lot of routings here, small gates, there are about like 30, 40 devices over here, transistors here, and they're connected. And the physical design part, the semi-custom, which is automated. So it goes from these gate netlists all the way to generating the layout and routing them, doing that automatically. So this is done automatically by the tool. So you have synthesis. The synthesis is doing the gate level netlist, but taking that, generating, do that. So basically the chip planning, the place and route, the routing, the clock tree synthesis, which all um, Puneet showed in the first day, is part of this physical design process. Okay. And then once you're done with this layout, like I showed in the previous slides, you're going to send it to the fabric. Actually, before I go here, everyone clear about the process from going from gate level to physical design, or any questions? Oh, actually, sorry. There was one question by Swadesh here. In which level custom design can be done, both circuit gate level and physical level? So this custom design is a flow. So like I'm explaining here, if you're doing what's called full custom design, right, you will not do RTL design, just like I'm explaining here, right? In a full custom design, you actually do the gate level netlist. So you actually take a schematic editor, start putting standard cell. You put AND gates, flip flops, like what it is done here, and you actually connect them manually, right? Just you do like in a breadboard, right? In a breadboard, you take the flip flops and join them. You basically do that. So you don't do RTL design. In full custom design, there is no RTL. Same thing with the layout. So when you're doing physical design, you do the complete layout by hand. You're not using any tool to automate the process. You might use the standard cells, which are already designed by the foundry house, but all the rest of the placement, you're doing chip planning, this and that, routing. If you have clock trees and all that, everything is done manually. So that's what's called full custom. So I think you're asking both gate level and physical level. Can you raise your hand so this maybe I can ask you exactly what you're asking? Yeah, go ahead.
Sir, actually, I am asking that whether, like you said, that there are certain tools that can automate the this physical design, right?
Right.
So I
Uh,
want,
so you're asking, is there a certain tool for physical design?
yes, sir.
Yeah. So a good question. So physical design, like I said, uh, if your physical design is a simple chip, you might be using one or two tools. So yes, there are certain tools to use. So even in a full custom design, right? If you're doing a full custom design where you're drawing in land, you still need a layout tool, right? So a layout tool is part of a physical design. So that's the bare minimum you need. You cannot start drawing layers by hand. That, that they used to do it when they were doing single transistor design. Obviously, you can't do that right now. So even for a full custom, very simple layout, you still need a layout editor, and that tool is for physical design. Once you get your circuit gets complex and complex, and when I show the steps which Puneet showed, like for example, doing chip partitioning, doing place and route, doing placement, doing routing, doing clock tree synthesis, doing timing. For as you get complex, there is a tool for each of these steps. They're all part of the physical design flow, but there is a certain tool for each particular process because they're so complicated, so huge, and so on. So for clock tree synthesis, for example, Cadence has a tool, Synopsys has a tool, Mentor Graphics has a tool, place and route, Synopsys has a tool, Cadence has a tool. So they all different types of vendors have different tools. I personally have always worked on analog domain, so we just do layout. I have never used place and route tools and clock tree synthesis and all that. But people who are doing digital design for any significant amount of complexity, there are certain tools. Same thing with front-end design. So front-end design, if your front-end design is as simple as just doing Verilog and doing synthesis, if it is a very simple synthesis, then the tools are very simple. If the synthesis is very, very complex, then the tools also get complex, and some of the tools will do partitioning first, they will do timing, what's called like pre-synthesis timing and all that before you do that. If your design is very simple, you can use a very simple synthesizer like YOSYS, like you guys did EDA Playground. So if you go to the EDA Playground, on the left side, you'll see synthesis. There's a tool called YOSYS. It's a free tool. You can play around with it, actually write a small code and do synthesis. You'll see it'll design it. Um, so yeah, so answer your question, physical design, there are, depending on if it is a full custom design, physical design means layout. That's it. You're just using a layout editor to do layout. If it is a simpler design, all it means it is you just do place and a little bit of routing. That's it. You don't do anything else. If it is the complex design, then your chip partitioning, your placement, your routing, your clock tree synthesis, your timing, everything is done through one tool, or sometimes one suite of tool will actually do it. Okay, did that answer your questions for this?
Yes, sir.
Okay, good. All right, any other questions? You have another questions for this? All right. Okay, so that's like very simplified flow of the entire process. Once you're done with this and you do post layout simulations like you did before and you're happy with that, what you do is you send these masks, which is essentially these layers of these layouts, to the foundry house. So wherever your foundry house is, um, be it TSMC or XFAB or IBM or Global Foundry, wherever it is, they will take your mass. And this process is what you'll hear in the industry a lot of times. People telling tape out, tape out, tape out. So this process here, sending this mass to the foundry house, is called tape out. And it's a legacy reason. When IC design first started, uh, it was actually physically sent to the foundries using tape drives, because that was the only memory then. So big tape drives, like you guys have probably never seen tapes, but they're size of wheels, basically car wheels, and they actually have magnetic tapes around it. So even a simple like transistor design, they will send it through tapes. And so when they say tape out, that means that tape was sent out. And that terminology has still remained. So even when you go into the VLSI industry, they'll say tape out, tape out. That's what it means. That means the data for manufacturing has been sent to the foundry house. Okay. And obviously the foundry house will take each of these layers, as I said, depending on your design, complexity of your design, these could be as little as 10 to 15 layers or as high as 200 to 300 layers. They will take each of these layers, convert them to mass, and they will use their uh, process steps to process. So like those few processing steps I showed, they'll go for each mass. And like I said, for each wafer. So let's say I have ordered 100,000 chips to the foundry house. So I'm selling, and I got an order from one of my vendors. They said, we need another million chips. So I said to foundry house, I need another million chip. They already have my data. Depending on the size of my chip, so let's say it requires 12 wafers, they'll put all the 12 wafers inside, and they'll take my mass, and these processes are obviously all automated. They'll go through this whole process: oxidation, etching, ion implementation, CVD, diffusion, and in the end, when the 12 wafers comes out, I'll have all the 1 million dies which are going to get packaged, cut, diced, and packaged into 1 million chips, and then they will deliver it to me, and then I can start selling them again. Okay. So that's the fabrication step. So this is like, you can, kind of like think of cooking. They have all the recipes. They just need your instructions on what to cook. Okay. If it is a RF chip, the cooking is different. I mean, the cooking process is same, but the steps are different. If it is a digital chip, the steps are different, and so on. So once it's processed, like I said, what you get is what's called a processed wafer. And you can see here, there are tiles of chips. These are obviously huge chips. These are probably processors. And they're going to cut and dice them in the foundry house itself. But before you do this, a lot of the companies where testing is very critical and expensive, they will do what's called wafer probe testing. Okay, so before they dice it, they will actually go into a wafer probe tester, and they have very fine probe tips, like 100 micron tips. They will actually go in, probe in, do the testing, and they will, and I keep saying dies, right? Diced into dies. That also has legacy reasons. So what before people used to do is, because this whole process is so expensive, they don't want to package bad parts, test it, and throw it, because that's expensive process. So they want to first find out what are the bad parts, because not all of the parts will come out good, because these are statistic processes. So let's say you have 1 million parts. Out of the 1 million, if your uh, yield is 99.9%, then 10,000 parts will be bad. So you want to throw those bad parts out. So what they'll do is they'll take this wafer, and then they'll do wafer level probing, where they'll probe with this like really micro probes and find out if your chip is working. If it is not, they'll mark that particular portion of the wafer with a dye, like an ink dye. Okay, so that's why it's called dyes. And then when they cut it and splice it, when you start packaging, whenever you see that ink dye, you'll just throw it off. You'll say, okay, this is a bad part. But sometimes the chip manufacturing, the packaging is very cheap, so they don't care. They say, no, just send it, we'll cut it and dice it, we'll test it at the package level, and if the part is bad, we'll just throw it at that time. So for example, this is a dice part. This might be like 10 millimeter by 10 millimeter or something like that. And then you take it, package it into a package, like I said, and you have to connect all uh, um, the pads to the leads, and then you can connect it from outside PCB, and like as I'd shown. So for example, in this case, the cell phone, you put it in the PCB, you connect them, and obviously before you put it in the cell phone, you have to test it. So you'll usually have test boards, you do your validation and all that. Okay, so maybe I'll just yeah, maybe I'll show you later on how the lead frame looks like. I wanted to put it. So essentially, these, you can't see them, but there are hundreds of pads in there. They're usually about 50 micrometer to 100 micrometer. Now, to give you an idea what, how much 100 micrometer is, um, your hair, if you take a cross section in general, some have thinner, some have thicker. If you take a cross section of your hair, typically it's about 100 micrometer diameter. If you have round hair, if you have square, then it'll be square hair. So so imagine, if you slice your hair, that's how small those pads are on these edges, right? And they could be even smaller, but that's typically how small it is. So you take fine wires, gold wires or copper wires, and you connect them to the lead frame, and the lead frame is this leads here. These are much bigger, which you can put it in the PCB, and maybe I'll show you a picture later on sometime to show you that. Okay, so you put it on, and that's how it gets connected to the outside world. Otherwise, I can't use the die just by itself. I have to package it, and what it is called bonding. So I take these wires, I bond them to those small tiny pads into the lead frame, and that's what gives me access to the chip. Okay, so this is like as I said, this is a very simplified digital design process. I mean, this is both custom and semi-custom, just that in semi-custom, these steps here, the verification and the physical design process, the RTL design and verification and physical design process, there are more sub-steps to it. Okay, other than that, pretty much everything remains the same. But the whole idea of the flow doesn't matter you're doing full custom, semi-custom, digital or analog, the basic steps are obviously the same. You know, you have to do a design, verify it, you have to have a layout. Is it automatically generated or manually generated? Doesn't matter. And you have to take these layers and send it to the foundry house. So ultimately, when the layers go to the foundry house, they don't care it's a digital chip, analog chip, RF chip, power amp, microphone, CMOS imager. They have no idea. They don't care. They just care that you have given them sets of all these nicely drawn polygons, rules specified by them, which are called DRM, design rule manuals, through their design rule manuals. And again, we'll go through that in a lot detail in our labs when we start doing our labs. Okay, any questions on these processes so far? Okay, hopefully you guys are understanding. All right, so what I'll do next is in next few minutes, I will show you the similarities between the design flow I'm showing you right now and what Puneet showed you in his slide. So that way, you know, you're not confused like, oh, what does this mean? What did he say? Um, so these were the pretty much the steps, the basic steps which were showed by Puneet on his first day. So where you went from idea system spec to architectural design and functional and logic design, which is basically your RTL design, and then circuit design, right? So this is what he called as the front end step. Actually, the front end step is pretty much this, but I've seen different people use different terms. So sometimes even synthesis, they'll call it front end. I call it, I coming from a custom background, call it back end. So these 4 steps is what I showed you in these 4 steps. So idea specification, the RTL design, verification, and synthesis is what he covered as these 4 steps. I hope that's clear. And then, like as I said, I was explaining to Swadesh right now, these 4 steps can be, depending on the complexity of the circuit, they can be uh, further granularized into these steps where you're going. The system spec is more like behavioral description. RTL is where you actually write your Verilog or your VHDL code, and functional verification is obviously you're functionally verifying your RTL or Verilog code. It's called functional because there is no circuit, there is no technology dependent thing, anything so far. And then, like I said, you do the logic synthesis, and from logic synthesis, actually the logic synthesis is the step which takes you from functional verification to get level netlist. Now there are tools where there are intermediate steps where I think they do formal verification, but honestly, I'm not 100% sure, why there would be another step between functional and get level nest, but that's essentially the synthesis step. And then you do the verification of the synthesized step. Like I was explaining in the previous slide, it's not guaranteed that if you have a behavioral description of your circuit that the synthesized circuit is one-to-one, right? As your circuit gets more and more complex, you might have more and more bugs in your gate level netlist. And this is something you need to verify after the synthesis, at the synthesis level. And as I was explaining in the previous slide, your behavioral description, and that behavioral description can be done purely in Verilog or system Verilog or system C, MATLAB, Simulink, any programming languages you can use to do Verilog different description, behavioral description. And that's obviously technology independent because you don't need to know what technology you're finally going to go into. You're just writing basically computer programs to write your behavioral code. Your RTL is the register transfer language, or whatever is your hardware description language. So now you, so basically the idea is, you have your idea here, and finally the foundry needs your mass, right? So you're going from here to here. If the design steps are simpler, your steps are fewer. If your design steps are if your design is complex, then those steps become more and more complex and granularized. But essentially, you're going to go from this idea to final to the mass. So you're traveling in that direction, right? So in this behavioral step, you had a very abstract description of your design using C or C++ or Verilog A or whatever system Verilog. Now you're taking it to another level of to your physical step, which is RTL. So RTL is still behavioral in nature, but at least now uh, it is event driven in the sense that you can have almost, depending on how you write it. If you write it in system Verilog, you can still have codes which cannot be synthesized. But typically when you write RTL, you write what's called synthesizable RTL code. So you're not writing any code which cannot be synthesized, like a printf statement. A printf statement is a valid system Verilog code, but obviously you can't synthesize it. But like a code which I showed you just before in the diagram where it says add positive edge, blah, 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 that is a synthesizable code, right? So it is getting closer to your physical circuit now. So your chances of getting a circuit out of this is now almost 90% or 99%, depending on the complexity of the circuit. So that's your RTL part. Functional verification is verifying that RTL code because you still don't have circuits. So that's all, as I was explaining, it's all technology independent. You don't need to know what technology you are finally going to fabricate. Okay. Next three steps in the front end part is technology dependent, as I was explaining, is that now you need to know which technology you're doing, because depending on that technology, your circuits are different, your timings, your parameters for those circuits are all different, right? So that's why you need to know what technology you are going to fabricate this in. And you'll hear a lot about standard cell libraries, and like I said, Santanu has a great lecture on it, and we'll look at some standard cell libraries of foundry houses, and they have what they call the timing data, which are usually captured in what's called .libs files. And using these files and design constraints. So design constraints are usually constraints which are given to the tool by the designer, saying these are my constraints. For example, let's say you're doing a clock chip, right? A simple clock chip where you take a bunch of inverters, connect them back to end, and you want to generate a 100 megahertz clock. So you give that as a design constraint, saying that I want to generate a 100 megahertz clock. My duty cycle is 50%. So each clock width is 500 nanosecond, but you have, how Puneet explained in detail, like, your setup and hold time of circuits and all that. So that's where you want to say this. So your setup and hold time in your flip-flops are whatever, 3 nanosecond, 4 nanosecond. So those are the constraints that will go into your tools. And on top of it, it will actually, unlike analog layout or for digital, in digital, they can actually estimate even the parasitic to a large extent. So basically they will say, okay, this is a simpler block. When it is going to lay out, probably the capacitance is going to be 10 microfarad. So they can actually figure that out from the routing files, and actually put those numbers from these standard cell library and timing libraries, and get a very close estimate. It's not going to be accurate, but very close estimate of what the timing is going to look like finally when it is synthesized. So those are the design constraints. So when the algorithm is trying to synthesize your circuit, it is using this constraint. Like, for example, it will synthesize and it'll find out that, oh, it's not meeting your timing requirement. So he might start inserting buffers or change the architecture or take the standard cell, which is not 1x but 2x, and start. This is all going automatically inside it. For a full custom guy, like when I'm doing full custom digital design, this is what I'm doing manually. I'm actually just doing spice level simulations and doing that, right? So those are the design constraints which goes into this process. And finally, you get a gate level netlist, and the tools are there to do the logic verification of the gate level using these .lib files, which are provided you by the foundry using these process design kits. Okay. So like I said, the steps are same. You're going from idea to a behavior to a little bit more concrete rather than being abstract. So you're writing RTL code instead of a C code. You're functionally verifying it. Now, once you're happy with it, you're saying, okay, I have a technology in mind. I'm going to synthesize it. So use a tool to do the synthesis, your gate level netlist, and your logic verification and test. Okay. So any questions so far on this one? This is a very important step because, you know, you're going to see in a lot of, you know, design flow documents or books where they're going to refer to this. So it's good to have an idea on what. So maybe just raise your hand. If you understand it so far, just raise your hand. Okay, good. All right. Look like most of you are getting the idea. But yeah, go back to Puneet's lecture or the first two chapters of both the books, Hodges and Kang, or the West, all the West and Ashragian, they all have a, oh, actually they're sorry, they have great introduction chapters, so you can refer to that. Not related to the topic, but how do they design such small things? Shima. Yeah, great question. That's what I kind of mentioned in the beginning, is that everything, all this is possible because of the processing steps, right? So the math they do, like if they want to do a 1 micron feature, they actually do 1 micron features and cut them using their photolithographic process. And they used to use UV, right? And people, obviously the UV, actually not UV, before UV, they're using a longer wavelength for photolithographic process. But obviously the limit was the wavelength of that light, and they could not manufacture those devices. So they kept improving. They started using UV. I think they use X-ray. So it's all processing steps. So how do they do it? I mean, you know, this is really a processing marvel. So you want to go into processing, you know, that, but it's a totally different area of design. So they are worried about photolithography, diffraction, gate length verification, this and that. So it's, you know, it's not design anymore. So yeah, it's all to do with processing. I hope that answered your question, Sumant. Okay. And Ashwini Kumar is asking, what's the difference between full custom and semi-custom design? Okay, well, that's what I'd been explaining, is in full custom, you pretty much, so in full custom, what you do is you design the circuit pretty much by hand, in the sense that you put devices or standard cells in your schematic editor, similar to using Spice. You lay out using a layout tool like Virtuoso Excel or Tanner Edit or whatever you're using, and that's it. When you go to semi-custom, a lot of these processes are actually automated. So use actually tools going from RTL design to gate level netlist. You use tools from gate level to do placement. You use tools to route them. You use tools to, what do you call it? Do clock tree synthesis. You use tool to extract the parasitics. And so, yeah. So the difference is semi-custom. From custom to semi-custom is basically how many steps you're using automatically, how many you're doing manually. So that's really the difference. So Srishti is asking, so what are the tools that generally use in logic synthesis? Yeah, so like for example, I personally don't use these tools, but um, Cadence uses Unovus to do logic synthesis. Um, in Mentor Graphics, they use a tool called Oasis. Synopsys, I think, is DC. Um, so yeah, so they're just different tools to uh, do synthesis. They're just names basically to me. If you still have a question, just raise your hand. I hope this answered some of your questions, Sumant, Ashwini, and Srishti. If you still have a question, you can answer. Raise your hand. I can unmute you. Okay. All right. So now I'll show you the backend part of it. So in backend part, I just showed that we are going to do physical design, which is, like I said, if you're doing full custom, all it means is you're doing layout. You're just putting P cells and um, just routing them. That's all. I mean, when I started layout, we didn't even have P cells. P cells is basically, it's a cell which all the layers of the transistors are already drawn for you. You're just putting them and routing them. When I started layout, we also usually what we'll do is we'll do the transistor, make a cell out of it, and just copy those cells out of it. So it's a very long, laborious process. But that time, we were doing few devices. Now you're doing, tens of thousands and hundreds of thousand devices. So it's all automated. So that's the physical design. So in Puneet's description, it was pretty much the same steps. So physical design, he also meant the same. Physical verification and sign off. Okay. So in custom design, all this means is like if I'm doing a like a small analog block, all this means is design rule check, which we call DRC, and LVS, layout versus schematic. So basically all it means is that whatever polygons I have drawn, they meet the design rules provided by the foundry. So if it is, really a simple foundry set, the design, I mean, if it is a simple, like for example, older technologies, let's say I'm doing 0.6 micron or 1 micron or half micron technology in XFAB, the design rules are very simple. There's typical design rules like minimum separation, minimum width, antenna rules, blah, blah, and all that. And it's very simple. And now if you take like the 4 nanometer, 70 nanometer design rule documents are like 600 pages. And so it's very complex. So the tools basically do that. So in a full custom design, the sign off means I'm just doing a DRC, and LVS is layout versus schematic. So DRC is design rule check. So in your labs, you're going to use Magic to do this. So you're going to use Magic to draw and do design rule check. And LVS is layout versus schematic. So you're going to use Magic, obviously, to do this. The popular tools in enterprise are Asura. Caliber is now kind of the industry enterprise standard. And then Asura has become actually PVS for Cadence. And then Tanner Mentor Graphics had their own, but they stopped that now. For layout versus schematic, again, you use Caliber or Asura. For your lab, you're going to use what's called NetGen. It's an open source tool. So the design rule check is basically saying whatever layout you have drawn, they are within the design rules specified by the foundry. The LVS is layout versus schematic is a tool which actually takes the layout, because remember, like I just said, the schematic has no physical meaning. Whereas when you draw physically, you want to make sure that that ultimately will fabricate the devices which are going to um, represent your schematic, right? So that's what the LVS is doing, layout versus schematic. It is basically saying that whatever layout you have done, it will extract all the devices using the LVS rule. So like, for example, your seniors right now who are in the job with Savia, they are in the PDK team. So they are going to write actually these rule files. So based on a polygon, like for example, if you have a polygon and if you draw a polygate on this, um, then this represents a transistor, right? This represents a transistor. So this is what the extraction tool will do. Like NetGen will extract these polygons into this tool. And then if you have drawn a schematic with this and the drain source and all that specified, then it'll say, oh yeah, this layout and your schematic actually matches. Okay, so that's what the layout. Now in big digital systems, um, so in big, just give me a second, guys. Okay, so there's a question here. In full custom still practice in the industry as it includes a lot of steps done manually? Yeah, question by Ashwin is that people do still full custom? Yes, of course. Like I was telling Puneet, I was working on an RF project which is 2 transistors. We designed it for like 2 years. Like RF power amp. Power amp is usually 2 devices, but people like there'll be a team of 15 people designing for 2 years. So yes, of course, people do custom design. All analog stuffs are mostly custom design. There is no automated. And like as I was mentioning in Puneet's lecture, there is no synthesis process in analog that doesn't exist. There's a small portion of it exists, but it's it's a very tiny portion. Most analog, you design the circuit and you have to do the manual layout. There is no synthesis process for it. Okay. And Satya Panda is asking, sir, which is more accurate or effective, full custom or semi-custom? Well, it's not about accuracy. It's about complexity of the design. And so ultimately you have to do the verification so that we'll make sure that it is accurate, right? So either be it full custom or it be semi-custom or full, fully automated, whatever the process is, your verification process doesn't change. Whatever you're going to use for verification. So for example, this custom verification here, this custom verification process here, it doesn't matter if you're doing custom or you're doing fully automated, there is a step you want to. So let's say, for example, you're doing SPI, right? Your verification is to make sure that you match the timing diagram of the protocol, right? The timing diagram which I showed you on the first slide. Now, if you use a automated process, then the circuit is synthesized automatically, but you still have to verify and make sure that it is meeting all the specs. Same thing. If I have a simple design and I do the layout and do the extraction, I want to make sure it still is meeting my timing requirement. If you do that process automatically, you still have to verify that it is meeting your timing requirement. So to answer your question, a short answer, both of them are accurate. Both of them need to be accurate. It's just that if your design is complex, then you digital and complex, then you want to do a full custom design, I mean semi-custom design, because otherwise it will take you forever to design that, right? If your design is simple or analog, for example, in analog there is no synthesis process, so you are doing full custom anyways, right? So you have to do that anyways. So the answer is, I mean, the answer is not that one is more accurate and one is less accurate. One is given a certain complexity, you just can't do it full custom because it will take you like a Intel chip. If you can do it full custom, but you'll probably be tapping out a chip every 50 years instead of every year. So that has to be done, semi-custom or fully automatic. Whereas if you doing a power amplifier, which is or LNA, low noise amplifier, you just can't do semi-custom. It's just two devices and it's all manual. Okay. So I hope it answered your question, Satya. If you didn't, just raise your hand. Okay, good. The other thing I wanted to say about the physical verification sign-off is, so this is for, so DRC LVS is, like I said, it's just purely for custom, which has to be done also for semi-custom. So it doesn't matter what you do, you have to do DRC and LVS for any complexity, any size, any design floor. The DRC LVS is a must. You have to do that. But on top of this, there are a lot of other verification sign-off, mainly what's called timing sign-off. Guys, just give me 1 second. Okay. Yeah, so in the physical design verification and sign-off, some extra steps are taken. One of the main one is timing sign-off, in the sense that the timings are done using tools. So there are a lot of timing verification tools which are used, like open source tool is like OpenSTA. So after the design is synthesized, the tool uses all the synthesis data, post layout and post P&R and post synthesis data, because now it has all the parasitic information and all that. So the timings are all going to be worse now than what it was before. And it is going to use that and still going to say that, yes, we are meeting timer. So it'll create a huge report. So usually there are a lot of physical verification designers. So this is a huge, so in India, for example, in VLSI design, probably the two biggest areas are the DV, the design verification in the front end. So this area, the verification area, and the physical verification sign-off, where people are just, and it doesn't mean you're just looking at the tool and saying, oh, it passes and all that. This is where you need your timing knowledge. So you'll get a report with, let's say, 10,000 errors, and you'll go in and you'll say, okay, this error came because there was a setup timing violation in this path. So I can put a buffer and do it. This the designer needs to fix. This we can probably waive it. So this you cannot do without having full knowledge of timing, like STA, timing data, and so on. Okay. So that's the extra time. So if you remember in Puneet's presentation, this physical design, like as I said, if it is complex, it has all these other steps which you have to go through. And the first step is partitioning, where you actually partition different parts of your blocks. You do chip planning. Place and route is basically saying, okay, the place, the standard cells in each of these partitioned objects needs to be placed and route. These are all done through tools or manually, depending again on the complexity of the circuit. Clock tree synthesis is basically routing the clock, because this is the most important part of the physical design part in what do you call it, in digital design synthesis part. And most of your timing errors and all that comes from either a poor synthesis or bad clock routing and so on. And once the clock is synthesized, then you do the routing for the rest of the blocks. And the timing closer is what I was just talking about, where you do the verification. So actually, this arrow I mean, what I've shown here should be more encapsulating this basically. So physical design and verification is capturing all this timing closure and everything. Okay, and this is all technology dependent. Okay, so there is no technology independent part. Once you come to physical design, that has to be. So if you're designing, so you have to have had decided by now what technology you're going to use, 130 nanometer or 60 nanometer or whatever it is you want to use. So that you should have decided by now. Okay. And here also you use a lot of the foundry files. One of the files is called the .left files. And this has what's called the standard cell abstracts. So when the tool is trying to do place and route, if it is uses the real layout to do it, it'll take forever because the data is so heavy. It has every micrometer data, right? The way the contacts and all that. But when when Santanu is going to teach you the standard cells, it'll show you that actually the standard cells are done with very rigorous regularity. So the left actually captures this regularity. It just tells you, okay, the cell is actually 10 micron by 40 micron. The VI is actually sitting at 1 by 1. And the place you can route is this region from 10 micron to 20 micron. So, and these are just text files. So they're just few kilobytes and the tool reads it and it can do the place and route before actually even touching any single layout. Because when you have a billion transistors, there's no way you can do that with real layouts because it'll just doesn't matter how fast a computer you have, it's just going to take forever, right? So those are, and then it has the .lib files which has all the timing data, and then it creates this what's called the SDF and other post layout data, which is essentially extracting the parasitics. Like in a full custom, when you're doing, it'll extract the parasitic and it will be a pure capacitance. It is a capacitance from this node to that node, this node to that node. Again, if you use this data, then it's you never be able to finish a timing closure. So what the tools do is they take this capacitance, they convert it into timing data. So for example, you have an inverter and the inverter has a propagation delay of, um, let's say 1 nanosecond or 100 picosecond, 0.1. So, and you do this gate level synthesis and it'll do a estimation saying that probably the capacitance is 1 femtofarad. So the delay is 110 picosecond and so on. And you do the timing analysis based on that. After it does the place and route and clock synthesis, signal routing and all that, there are tools which will extract, but now the extraction done is the SDF file, which actually just tells you the delay. The delay will be now, it'll be like, okay, no, it's not 102 now because there was a long route. It's actually 150 picosecond. And because of that, your entire timing is off completely. And that's also part of a file which is generated during this physical design process. Okay. Any questions on the backend part? I hope this is all clear. Like I said, I tried to. Okay, so there's a question from Swedish. It says, sir, if in a circuit block the delay is changing randomly, how to synchronize your clock with that signal? Well, it will not change randomly because once the layout is done and everything is done, um, it is bounded. So let me put it this way. It is bounded in the sense that, so let's take an example of an inverter. If you have an inverter and like I gave you an example, after post layout, it turned out that the delay was 150 picosecond. Now they're bounded because of temperature and process. Okay. So yeah, like max and min delay. So you have a max and a min delay. So basically it is saying that the process is going to change, process in the change. So I told you, right? A wafer is going to come out and I'm going to have 1 million devices. Now that inverter might have 100 picosecond for those 1 million devices. Tomorrow I go and order, a wafer comes out, I get 1 million chips, but now it is 90 picosecond because those are the variability of the process, which I have to design within. 3 years later, I order another 1 million chips from the foundry. It comes and I found that it's actually 200 picosecond. Okay. So I have to design for the maximum. So process variation is one, and then it could be data dependent also. What I mean by data dependent is when we do combination logic, you'll realize that a NAND gate, for example, depending if one of its input is high or low, the other input going from low to high, the propagation delay will be different because the RC delay is different. It'll be clear when when we do the delays. Now, the delay will change depending on the data, but you design it for worst case, right? Because you don't know what the delay is going to be. So all this timing sign off, which I'm showing here, they are meant for worst case delays. Okay. So basically, you design for worst case delays. So all your temperatures and process variation, data dependency, and whatever it is there, once you know what the delays are for that, you design it for the worst case delay. Okay. So now after that, if it is changing with temperature and you're changing with data and all that, it is all, they are not random in nature, right? They're actually deterministic because you had already determined that your maximum delay would be that much. So is that clear, Swadesh? If it's still not clear, raise your hand. So yeah, so all the timing and all the verification which is done is actually done for worst case delays. Yeah, like max and min delay as you're pointing out. Okay, so I just wanted to quickly show that I think a lot of you are asking what's the difference between semi-custom and full custom. So I just made a one-to-one. So specification which you have is obviously the same. The architectural phase which we do in full custom, that's also there actually in semi-custom as well. So, so where you're doing your RTL design and verifying, so that could be these two steps. Circuit design is what is a part of synthesis, and like as I said, one is not accurate than the other. It's just that one is just a different way of doing it, but you still have to meet the same specification. You can't avoid the specification, and in some cases you cannot do semi-custom, like in analog design you cannot do semi-custom. Layout design, like I have been saying, corresponds to the physical design, and fabrication corresponds to the fabrication step, obviously. Okay, so that's all I have for for this lecture. I was planning to take 10-15 minutes break, but decided to just go one go. So we finished a little early.